The central tension of statistics lies in a simple problem: making definitive claims about massive populations using only limited sample data. To navigate this, we attempt to estimate one specific value, the true unknown population proportion, represented mathematically as p. Our calculation begins with the sample proportion, or p hat. This is the point estimate, our single best guess for the larger population. We rely on p hat because it is an unbiased estimator. Its sampling distribution naturally centers on and targets the actual true parameter we are seeking. However, a lone point estimate provides zero context regarding its own accuracy. By itself, it offers no way to account for the potential for error. If a point estimate cannot tell us how far it might be from the truth, how can we rely on it to drive a conclusion? Rigorous analysis requires that we find a way to quantify our inherent uncertainty. We solve this by constructing a confidence interval. This is a calculated range of values designed to bracket the true population parameter. Shifting from a point estimate to a confidence interval allows us to move beyond a single data point and establish a range that defines our mathematical certainty. This calculation starts with a chosen confidence level, represented as 1 minus alpha. A 95% confidence level, where alpha equals 0.05, serves as the standard baseline in scientific research. This percentage maps onto the standard normal distribution curve. We use critical values, denoted as z sub alpha over 2, as markers to separate typical results from significant outliers. This chart shows a 95% confidence level geometric boundary. The central shaded area holds 95%, leaving alpha split into 0.025 tails. Critical z-scores are negative and positive 1.96. Adjusting to 90% shifts the value to 1.645. Demanding 99% expands it to 2.575. These critical values calculate the margin of error, or E. It is the maximum likely amount our sample statistic will miss the true parameter. The formula for E is the critical value multiplied by the estimated standard deviation of sample proportions. The margin of error is not an arbitrary cushion. It is a rigid mathematical boundary dictated by the exact level of confidence the researcher chooses to demand. Before calculating an interval, the data must meet specific prerequisites. It must come from a simple random sample, and the trials must satisfy the conditions of a binomial distribution. Additionally, the sample must contain at least 5 successes and at least 5 failures. Consider a Sallie Mae survey regarding online education. They polled 950 undergraduate college students and found that 53% of them take online courses. Verifying the requirements, 53% of 950 yields 504 successes and 446 failures, both exceeding 5. Inputting our 1.96 critical value, standard deviation, and sample size, the margin of error is 0.0317. Applying this to our 0.53 estimate establishes limits from 0.498 to 0.562. While understanding this manual derivation is important, modern researchers rely heavily on computer technology to execute these complex algorithms instantly. This software display shows the automated output for our survey parameters, confirming the manually derived interval of 0.498 to 0.562. While deriving these limits is straightforward, the true vulnerability of a study often lies in how those results are interpreted. There is a common trap in how we verbalize these results. It is incorrect to say there is a 95% chance that the true proportion falls between these numbers. The true population parameter is a static, unchanging fact. Once our specific interval is calculated, it either successfully captured that number or it did not. The probability for that specific interval is either 1 or 0. This plot visualizes 95. For instance, a study in the Journal of the American Medical Association on nicotine patch therapy reported a 95% confidence interval spanning from 58% to 81%. We extract the point estimate, p hat, by averaging the upper and lower limits. Adding 0.81 and 0.58 and dividing by 2 reveals 69.5. The second is used when no prior data exists, replacing estimated proportions with a mathematical constant of 0.25. Both equations follow a strict round-off rule. Calculated sample sizes must always be rounded up to the next whole number to ensure a sufficient sample. Let's apply this to a real scenario. Imagine designing a new survey aiming for a maximum 3% margin of error at a 95% confidence level. If researchers use a prior estimate of 79%, they plug that value into the first formula. The calculation dictates a minimum of 709 adults. Without prior knowledge, researchers must use the 0.25 constant. This forces the minimum sample size up to 1,068 adults. Notably, the total size of the population does not appear in these equations. The reliability of a poll depends primarily on the sampling method and the sample size. Lacking prior data forces researchers to collect significantly larger samples to achieve the same level of mathematical confidence. The walled confidence interval method detailed today is primarily an approximation used as a foundational teaching tool. Statisticians often use the +4 method as an alternative. By adding 2 successes and 2 failures to the data, this method keeps the coverage probability closer to the selected confidence level. For advanced rigor, researchers utilize tools like the Wilson score and the Klopper-Pearson methods, which are built directly on the exact binomial distribution. Whether using the walled approximation or advanced algorithms, the goal remains the same: taking raw sample data and defining precise mathematical boundaries of our uncertainty.